Well, that's where we finish the discussion for acceptance rejection method. Of course, we have the multiplication for majorizing function t, right? So this one, t. Previously, we have the horizontal line to represent t, and later we can let you know, if possible, you can try to find a better one. For example, this one. As for how to choose, actually, you need to have some extra technique to help you to find properly the function, majorizing function t. Right now, we have another way to improve the acceptance rejection. Actually, we have f, and f actually is the original one. So f usually it should be complicated function. All right. For the complicated function, maybe still can have the proper calculation. However, in the following, we try to have the multiplication. And such a multiplication is called the squeeze methods. How to have the multiplication? We can have a fast pretest. Okay, fast pretest for acceptance. Acceptance before step 3. So how to do? In fact, we can have another function, minorizing function, b. So previously we have a majorizing function t, and right now we have a minorizing function b. Minorizing function b says b of x lower than or equal to f of x. Here, this one. All right. And right now, let us look at the acceptance rejection method again. So let me jump to the algorithm. So this algorithm, acceptance rejection algorithm, we have y, of course, based on r of x from t of x, right? And also we have u. And this u independent of y. We want to check u lower than or equal to f over t. If yes, this is acceptance. Acceptance, then we can return this value y to be the value for x, or otherwise we need to go back to step 1 and retry. Okay, so this is the acceptance rejection algorithm, and right now we want to improve this part if f is complicated. Well, u lower than or equal to f. It is f. But right now, majorizing function b. If u lower than f, and then we can accept. And right now, we have a simple, at least should be simple, b of x. And also, we have a u lower than or equal to b over t. Well, if this condition meets, that says the previous condition u lower than or equal to f over t meets as well. So that's why if we can check this one meets, and then we can accept right away, right? So this is a modification. It is called the pretest. Well, if this not meet, if not, and then we need to go on, right? And do the actual test in step 3. That is the previous step 3. If we can have this, and then everything's okay to have the pretest. And this pretest, maybe we have an easier function b, not the complicated function f. All right, as for how to choose, in fact, we try to have B close to F, and also B will be easy, right? Easy and fast to evaluate. So this one squeeze method, perhaps we don't have some maybe not actually speed actually the shorten the speed, maybe not shorten the time and speed up, maybe not, but at least we expect fast and easy, and so that we can have another multiplication, and such a multiplication we call the squeeze method. All right. Okay, so this is the squeeze method to further enhance acceptance rejection. About this, any question? I think this one, if you want to do, you can try. Actually, if you don't think it's really easy, maybe you can skip. So even you try to choose fast and easy B of X to maybe to facilitate the acceptance rejection algorithm, but sometimes we don't have this multiplication. All right, so this is the squeeze method. And right now, then I have another one. Actually, this one perhaps not included in our previous agenda, but in the task we have this one. However, this one, it is somewhat complicated. You can refer to page 448 to 449. Why? Because this one not really easy. So I think you can refer to the 2 pages on the task. Actually, you can refer to the 2 pages in the task book. And then you can have the ratio of uniform method. As for the details, I think you can refer to the 2 pages. Right now, we have the brief introduction to this ratio of uniform method. It is developed by Kinderman and Monohan in 1977. Okay, and in fact, if we have the details, this one, even the detail, this one, however, we still have more details, so you need to refer to the 2 pages to have all the details. For example, here, this is the inf, and this is actually this should be soup, and this is the inf. So not really easy. Even we have the algorithm, it is not clear. You need to refer to the task book to have some other details, and so that you can implement this algorithm. But at least we have a UMV and we have the ratio. So that's why based on the relationship of the variables, UMV and the ratio of the 2 variables. And in fact, UMV will be uniform, right? And we have the ratio. Okay, so this is a ratio of uniform method. Sometimes maybe we may have these for which one. In fact, you can you use this one to generate Cauchy random variable. Possibly can apply these. Okay, so this one we seldom use it. So I just let you know we have a ratio of uniform, and this method apply to generate Cauchy distribution. So you can use this one to have the Cauchy random variable. And after that one, in fact, we still have another one for normal, but right now that I have this one first. Special property. For special property, let us look at this geometry. If we have a geometry, then we have a geometry. then we can have the story. X follows geometry, so X should be the story, or like this story. Number of failures before the first success in Bernoulli trials, right? And actually, we can have another geometry. Number of failures plus the first success is another version. I let you know this version as well. But right now, we focus on the version covered in the textbook that says the number of failures before the first success in Bernoulli trials. Okay, so if we have these, you can try to follow the story to generate geometry. So to generate geometry, you can have Bernoulli and try, and then you can collect the number of failures before the first success. If you have this value, then you can use this value to serve as the value for geometry. And you have this property. How about the efficiency? Actually, sometimes the efficiency is not good. Why? If we have a really low P, and then we should have a large number of failures. Okay, a large number of failures, so you need to try for a long time. Actually, for a long time. If we compare the time to a large P. So this one, even we know the story and we can have the generation of geometry, but sometimes it is not efficient. Okay, in particular, if a P is really low. All right. Okay, so this is the first one, geometry. And actually, special property, it says we have many stories, and these stories serve as the special properties. So that's why we call this method as special properties. And you can look at these. How about beta? Beta, in fact, you can refer to chapter 6, and then you will have the story. If we have gamma and gamma, then the ratio here meet beta with 2 parameters. Okay. So this one you can refer to chapter 6. Then you will have the story. And actually, you can have the others. And then you can have the special property. So how to have the special properties? I think you can refer to chapter 6. From those tables, you can have the special properties. Okay, so in the following, we want to apply general approaches to generate random variates. First of all, we want to check how to generate continuous random variates and then discrete random variates. And actually, we can generate the empirical random variates. But let us have the 2 categories, and that we can include the empirical one in some of the content. Well, right now, general approaches to generate random variates. So we have many choices if possible, right? And right now, we look at which one will be the suitable one, and then we apply that one for the generation of the random variates. First of all, uniform. Uniform, actually, we have this. U from A to B, this one. If I want to have this one based on U from 0 to 1, then how to do? Okay, actually, we have an inverse transform. inverse transform with the inverse function here. It says a plus b minus a multiply u. Why? So you can try to solve it. Well, originally we have, in fact, you can refer to the table. But right now, look at these. Right? So how about these? So if we try to derive these, I mean, right now I derive it. Okay. So if we have a, then we have 0. So this one should be these. Right? So finally, we have these. Right? In fact, you can refer to the table. I just want to let you know we have f here. If we have f here, how to derive inverse function? You need to set it to u. So you have these x equal to these. Right? So this one, the same. Well, I just retry the inverse transform. So that says if necessary, you can apply inverse transform easily, right? Okay, so this is the uniform, and I retry the inverse transform and provide you some of the details. And so that we have this algorithm, generate u and return x by using the function, and so that we have the continuous uniform distribution. Okay, that's it. So this is uniform. Any questions? I think it's easy, right? And actually, I derive f CDF here based on the initial PDF. So sometimes if you need to derive CDF from PDF, I think you can do it. And also, if we want to have the inverse transform, you can try this one, and so that you can have the inverse function. Once you have the inverse function, and then you have the algorithm easily. Okay, that's it. So uniform. Is it okay? I think no problem for you guys, right? The next one. In the following, we will have the results. And if necessary, you can try. And I just have the way to generate this variable, and later we can check. So first of all, exponential. Previously, we've known you can use inverse transform. So okay for this, right? For other, actually, we can pass on exponential so that we have a sum, and so that we have a convolution, right? As for this, I think up to you if you want to try. And gamma, actually, we use acceptance rejection. Acceptance rejection discussed on pages 453 and 456. So we have AR for gamma. And where about, again, we can have the inverse transform, and later we can check it. So we just let you know how to have the method to generate these variables. For exponential and for m-stage order, we can have the results directly because we've ever derived exponential. M-stage order, actually, we can have in fact, it is the special property. The special property applies sum of exponential to reach m-stage order. And normal, in fact, it is a new method. Okay, we can have two methods to generate normal. Box-Muller method or polar method. So we have two ways to generate. As for Barth-Muller method, not included in our previous method, and the same polar method not included in our previous discussion, but actually it's okay to apply the two to generate normal. And later we can see one of them. Okay, so you can use Google to have the algorithm to generate normal by using Barth-Muller or using polar method. And the log normal, what is the method? Actually, you can call this is a special property. We can generate normal and follow the special property exponential of y, and then this is the log normal. However, if we have these, we need to properly map parameters for log normal to normal, right? Here we just let you know if we have a normal using exponential of this normal, then we have a log normal. Why? Taking logarithm and this one follows normal, then this variable should be log normal. And actually beta use the previous special property. Okay, so it's exponential. I think we know this. Actually, we've known. So I do not repeat. You can check it. Inverse transform, right? So finally, this is an algorithm. Right? If you don't want to know, you can apply for sure, right? So at least I let you know the algorithm here for exponential. M-Allen. Previously, we have the discussion. We can use sum of exponential to reach M-Allen. And so that we have the algorithm here. It is called the convolution, right? I think this one discussed previously, so I go through it quickly. And gamma, actually we use AR. Acceptance rejection. Okay, and right now I do not discuss in detail, but at least I have the scan pages for gamma from the textbook, so you can look at these. But we have two cases. This is the first case to find the majorizing function t. If we have that one, when alpha fall within this case, then we have the algorithm. All right, so this is the algorithm from AR. And another case, we have this. Likewise, you can have a T. And finally, we have R of X here. And so that we have the algorithm. About this, I think it pretty depends, right? Because we need to choose majorizing function. And of course, the textbook that they have the majorizing function for the two cases, alpha lower than 1 or alpha lower than or equal to 1 and alpha greater than 1, and so that we have the 2. For this, I think I skip all the details. I think you can refer to the textbook, or maybe you can refer to the current pages to know we can pass on the selected majorizing function, and so that we have the algorithm to generate gamma. And that's all. So this is gamma. As for whereabout, you can try. Actually, not really difficult, but you can try. So that you can find the inverse function for whereabout distribution. If we have this for whereabout distribution, the same. 1 minus u, we can replace by u. So that's why we have a u directly. So you can have this. If you want to generate about, right? About the division for these, I think I skip it so that you can try. And once you try, I think you will have the inverse function. And with the inverse function, we can easily have the inverse transform method, right? Well, about normal. We already have the polar method. Actually, you can have the Box-Muller method, right? But we already have the polar method. If we apply polar method, we have these. So why we can apply these to generate these? In fact, you need to refer to the polar method. Okay, as for the polar method, you can use Google to find all the details. I think I skip the details at this moment. Well, this one I think we do not discuss. I mean, we do not discuss in the previous slides. But actually, it's a new method, so you need to use Google to find it. And so that we apply polar method to generate normal. Well, at least we already know we can have Box-Muller or polar method. So can we have the other method? Actually, no, because of no. So that's why we have the actual method, Box-Muller, Box and Muller, and the polar method. Okay, so here it is called the polar method for the normal random variable. Well, log normal. Previously, we have the algorithm already. But if we want to have the proper parameters, you need to map the parameter. So here, we have the story to map the parameter. Okay, so the parameter for log normal and map it to the parameter of normal. So you can have the proper formula to map the formula for log normal to the parameter for normal. And once you have the proper mapping, and then assume we have the parameter for mu and sigma square for normal, and then we have the generation for log normal properly, because we need to meet the parameter for the original log normal. Okay, so for this, I think you can refer to Chapter 6 to have some parameters. And so that you can have the formula. So that's why I let you know you need to use the formula for log normal and map it to normal. And so that you have these. I think you can try by yourself, or you can refer to chapter 6. Then you have the two equations. Solve the two equations, then you can have the parameter for normal. Okay, so that's it. I skip some of the details, but at least I mentioned. You can use the two relationship to derive the parameter to normal. Once you have the two parameters of normal, then you can have the generation for log normal. Well, let me stop here and let you guys to think about the current generation of random variables. Is it okay? So think about this for a few minutes. So check it. If you have any question, you just let me know. So maybe let me have 2 minutes for you first. And if any question, you just let me know. If no, and later we can continue. So I think you gotta check it for yourself. So, any questions? If yes, you can let me know. Okay, go ahead. Of course, let me try to nominate and so that check again. So first of all, Diego, any questions? Okay. I think at this moment it will be easy. So you just follow the discussion and check all the details. And actually, I skip some of the details. For example, the mapping of log normal and the majorizing function for gamma. I think you just follow the discussion in the task force, then you will know the details for log normal and gamma. And beta actually is a special property, this one, right? So I think it's really easy. So I go through these directly. And in fact, you can try to check the others. Actually, the others, we have the special property. Special property. However, for log logistic, we can use inverse transform. And I do not carry out how to have the algorithm, but you can try. Inverse transform for log logistic. So how to do it? And here, special property. Special property. Well, that's all. So for the well-known distributions, we have the possible method. Unless some of them we cannot apply, so we can use Box and Muller or polar method for normal. And actually, for ratio of uniforms, we can apply that one for Cauchy random variable. Unfortunately, we do not include Cauchy random variable, so we do not use that one. Use ratios of uniform to generate Cauchy. In fact, if you want to know how to do, you can use Google to have Cauchy and ratios of uniform. Then you will have all the details to generate Cauchy random variable. All right, and finally we have this one, triangular. For triangular, I think from the previous discussion, we have many methods. We can use composition. We can use inverse transform. And we can have the others. As I remember, we can have 3 methods, right? Here we have the inverse transform. So you can try. Why? We can have this form for the inverse transform. Again, I skip it. At this, I let you know you can apply the inverse transform algorithm to generate the triangular random variates. Okay, so that's all. And in fact, previously we did not that you know how to generate empirical distribution, but actually we can have. Why? Actually, we need to know the relationship. I think if you can refer to the previous way to generate the actually not generate, actually you know the relationship, then you can have it. So this is a way inverse transform and the same inverse transform. So refer to the previous empirical distribution. I think it will be easier to have these, and so that you can generate the two for the two empirical distributions. And likewise, I think this one, it will be easier because it is the inverse transform. You just follow the interpolation method to have some relationship. Once you have the relationship, then you can have the derivations. That's all for the empirical distributions. Well, I do not have the detailed discussion, but you guys can check it. Okay, so that's all. So up to now, we finished the discussion for continuous random variable and also the empirical distributions. And still, maybe you have the same thoughts to derive discrete random variables. If you think so, then it is a different story. So right now, let us have the discussion for the different story for discrete random variables. In fact, you have the discrete inverse transform, so I think that's fine. But right now, we do not focus on the inverse transform only. And we have a new method later called Alice method. Okay, called Alice method. Alice method, it is initially developed by Walker in 1977, and later it is refined. Okay, actually, it was refined by Cromwell and Peterson in 2 years later. Okay, so this is the Alice method. Alice method, why we want to apply Alice method? In fact, Alice method, it is a version. Discrete acceptance rejection algorithm. Maybe not called discrete. Actually, it is an acceptance rejection method for the discrete random variables with the proper modification to remove rejection. Okay, to remove the rejection and so that have acceptance simply. So it says this is AR. It can be used for generating any discrete random variables. Okay. And also you can have the composition for the discrete, but right now we don't discuss it further. Well, right now, let us have the general discussion for arbitrary discrete distribution. So someone like from scratch, we try to discuss how to have the generation for the discrete random variables. Which one? Right now, it is a general one, so we do not focus on the specific one. So that's why we call arbitrary discrete distribution. Well, what kind of arbitrary discrete distribution? This one. We have random variables. Right now, focus on the random variable from 0 to n. And of course, we have the corresponding PMF. Well, if we have this initially, in fact, we can map it to the general one. For example, we have the mapping. Okay. Well, if we have the mapping, then if you have this mapping, how many? So you have 0 to 1 and n to m to m, oh, sorry, n to n mapped to n minus 1. So we have these. Okay. So if we have the generation, then actually we have the mapping. If you have the mapping and then you just follow the mapping. So that's why we assume we can generate J for the previous discussion with J, and then we have the mapping map to the value X. Map to the value of X if we have the current way of numbering from 1 to m. So you can have J plus 1, right? So this one, just let you know, if possible, apply the mapping. If possible, we can simply discuss the special one. So it doesn't mean we want to have the arbitrary discrete distribution for our focus. Actually, we have the special case for discrete distribution. If we have a value from 0, 1 to n, okay, so in the following, we will focus on this case. Okay, so follow the case, and we can have the first simple case, 0, 1, 2, 2, 3. And if we have the given probabilities, if we have these, and we have 2 plus decimal, okay, 2 plus decimal, 2, right? 2 plus decimal. So we can try to use memory. Okay, the memory, set the memory to store 0 using 50. And the next 20 memory to store 1, and etc. 37 to store 2, and 28 to store 3. That says among 100. For example, you have 100. Maybe here we can call variables, even not variables, but at least variable to store, or maybe the elements in the array. Okay, so you can have 100 variable or 100 elements in the array to store the value for 1 and 2 and 3. Sorry, 0, 1, and 2 and 3, using the way these represent the number of these values. If so, then we can apply the algorithm. What kind of algorithm? We choose one. So we can use uniform. Okay. So uniform, previously we already know this is a way to generate uniform. Even right now, we try to have the generation of a discrete, but we treat this one given. So we can have this one, right? Once we have these, we can return value by looking up the content of the element. Okay, so if we have the way, and then we can generate these discrete random variable. Is it correct? Why? If we have the way, and then we have the algorithm valid for this one, it's really easy if we have a uniform and taking the value. So we simply have the uniform approach. So we have a probability for P0 by using 15. Why? Because 15 among 100 elements, we can have a value 0. So that's why this is a probability. So the probability actually meet the original setting, 0.15, right? So that's why we can use a way. If we have the way, we need to look up the value, right? If you look up the value, and then this method is called table lookup. Where we have the table, actually it's the memory. Okay, here we call vectors, right? So we can have the size 100 of the vector. Maybe you can call this is array. Using the vector, using the array by looking up the value with the selected index j, and then you can have the generation of this random variable, discrete random variable. If we have this way, table lookup, so really simple, right? And right now, consider 2+ decimal. It will be fast, no problem. However, apply the method, we need to check the number of decimal, right? So how about 3? And how about 4? If we have 3 or 4, then we need to apply, actually we need to have a large size array or memory. So that's why about the storage, it depends on the number of decimals. If we have a large place decimal, and then we need to have a large space. So large space, then we try to have the multiplication. So how to do? Later we have a modified one. It is called Marsaglia tables. For Marsaglia table, actually we still pass on 2, but we try to save space. Well, how to save space? Later we can let you know. Before we discuss it, let's take a rest, because right now it's a time to take a rest. So let me stop here. And before taking a rest, so I check up to now any question. If no questions, let us take a break. Okay, for 5 minutes. Okay, that's it. Take a rest.